Now we're going to look at graphing simple harmonic motion. So touched on graphs and SHM a little bit. We had a question or an example a little while ago that was, what would a graph of acceleration against displacement be? And that was just a sort of a directly proportional line with a negative gradient. But what if we sort of looked about what was happening to the displacement and the velocities over a certain length of time? What would a displacement time graph look like? So I'm going to ask you first of all to get a bit of paper and sketch yourself some axes, displacement and time, like the stuff you see on the screen in front of you. And I'm going to say I would like you to sketch this. Here's my pendulum. I'm going to start off with a positive displacement. There you go, there's my positive displacement. I'm going to let go of it and I'm going to let it swing for 2 or 3 complete oscillations. I would like you to sketch a graph, we don't need any values, of what you think the displacement time graph would look like. Go ahead. And welcome back. So, couple of things. I was very careful to say that I'm starting with a positive displacement. If you study maths, or it possibly is only in further maths, I'm not sure, I can't remember now. When you look at oscillations, they don't really require you to start at a particular point. But we keep it simple in physics at the moment, take it a bit further later on, and we say we always start with a positive displacement. So your graph should start up here somewhere. And now I want to think, what have you drawn? Okay, so it starts displaced to one side. After a while, it goes back through the rest position, then it goes past the rest position and goes to a maximum negative displacement, then back to the rest position. Bosh, here we go. This sort of thing is happening. So it's a harmonic pattern, up and down, but you need to ask yourself, what's happening here? Is it, are you connecting this up with straight lines? Whoa, that's not a straight line. Okay, that scared me. Straight lines, like this. Normally when I do this in class, a couple of people will sketch it with straight lines. But you need to sort of, if you have done this, you need to think to yourself, what does this actually show you that basically tells you instantly that it's wrong? I'm going to put a big cross up here just to prove that it's wrong. The thing that's like a red flag to me is that I know on a displacement time graph, a straight line means constant velocity. So if you've plotted or sketched something like this, definitely wrong, because you're saying it's going at a constant velocity and then suddenly going at another constant velocity. So it would be like this. Instead of just coming to a stop and going fast and kind of, you're saying it goes bop, 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 at a constant velocity each time. And no, it's not. So we need curves. And in fact, it's going to look like, well, why don't I just show you this, a sinusoidal curve. So your displacement time graph should look something like this. Well, that's embarrassing. There's now someone at my front door. I'll just ignore that for a second. Okay, right, carrying on. So what I'd like you to do now is get yourself a piece of paper. If you've got graph paper, that would be amazing. If you've got squared paper, that would be equally fantastic. If you haven't, it's not the end of the world. But I'd like you to just draw out some axes for yourself like this. I'm going to be quite prescriptive about it. I want you to draw 3 sets of axes directly above each other, nice and neat, and on one of them I want a displacement time graph, the second one a velocity time graph, and the final one an acceleration time graph. Whoops. Hang on. Here we go. So what I want you to sort of do is a bit like this, is underneath your displacement time graph, I'd like you to attempt to sketch the velocity time graph that goes with it. And if you find that very straightforward, go on and do an acceleration time graph. That will take you a little while to think about, and maybe before you do it, think back to everything you know about displacement, well, basically motion time graphs from year 12, what the gradients of the line tell you, because that could be very useful. So over to you for a couple of minutes. That'll take a little while to do neatly. And I will sit here for a second. I'll have a drink. That's better. Okay, welcome back. So historically, when I've taught this to people, people have found it very challenging to get right first time. One of the reasons is that they don't really think back to stuff they know from year 12. This time I can't see what you've done, so I can't actually watch you make the mistakes, but I can anticipate them. So let's have a look. Right. Let's start just by looking at the displacement time graph and translating it into a velocity time graph. Now let me just see whether I can do this. Right, I can. So one of the things we can do is go back all the way to this that we did last time, where we said that, oh, okay, when we have a maximum positive displacement, the velocity is at a minimum, the velocity is 0. So we can, in fact I could do that on this one here, I can say to my, actually I won't do it on that one because it's not very clear. Okay, I can say that for my velocity time graph, where the displacement, in fact let's do this. You shouldn't do it this way because it becomes very messy, but I'm going to draw over the top of this one. So in my red, I'm going to make it a velocity time graph. So when there was a maximum positive displacement, the velocity was 0. So I'm going to mark a dot there. Right. Next thing, going back to your notes from last time, is when the displacement was 0, basically the rest position, it was at its very fastest. But starting from a positive displacement, the first thing that the velocity does, it gets increasingly negative. So when the displacement 0, the velocity is at a maximum negative value. And then, as we go out all the way to the other side, the velocity goes back to 0 again. We follow that same logic through, and we get up to here, and I'm going to click up here. When the displacement 0, we have a maximum velocity, and it's positive. Now that's just going back to the stuff from last time. I think there's an easier way, and the easier way is using what you know about displacement time graphs. I'll just get myself a different tool. What colour do I like today? Orange. And you know the gradient of a displacement time graph. Go away. The gradient of a displacement time graph tells you the velocity. So look, at the top here, oh, it didn't let me do it. Sorry about that. The gradient here is 0, so the velocity is 0. The gradient at this point here is at its maximum negative value. So there you go, you've got a negative value. The gradient here is back to, sorry about this, I need to lock this in place. See if I can remember how to do that. I don't know what I just did then. I'm going to pretend that didn't happen. Let's try this. Lock in, I used the wrong shortcut. Okay, go back to this one. Here we go, sorry about that. Okay, so here we're back to, it's gone black. A zero gradient, so zero velocity, and then at this point here, we've got the maximum positive gradient. That's the maximum positive velocity. So that's become horribly messy. So underneath here, there's one that I prepared earlier. And does this let me scroll up? Yes, it does. So a velocity time graph basically looks like this. If we start here with this one being a cos, basically a cos graph, isn't it? The velocity time graph is like a negative sine graph. And then you could follow exactly the same process to establish what the acceleration time graph is. Remember the acceleration, again, the gradient at each point on this line tells you the acceleration, or you can pick key points and go back to the stuff we did last time and use that to figure out what the graph should look like. I'll leave that with you for a minute and you can try it out. So here's the time I'm pausing. And I'm back. So this is what the acceleration time graph would look like. And it's basic. Oh, well, my head's over it, so that's not helping you, is it? So let's move my head out of the way. Okay. So the acceleration time graph is basically a mirror image of the displacement time graph in the x-axis. And that makes sense because, that makes sense because if we go back to this thing, the accelerations were a mirror image of the displacements. When the displacement was maximum, the acceleration was at a minimum. Same at the other side. So that is it. Whoopsie. I've given a click into the future there. That is it for the graphs. We will move on from this to look at equations and calculations using simple harmonic motion. But what I want you to do now is, you've probably got scraps of paper with this on. You need to be able to draw these very neatly and be able to sort of just do this on demand, because it's a very common exam question. So that is your next task. Next week we'll have the equations. I will have some questions for you to do on Google Classroom. So long everybody, goodbye.